Hello everyone, welcome to Pratibha Tech. In this video, we will solve the problem of the day question on Geeks for Geeks for 20th April 2023. The problem statement for today is Bheem wants Ladoos. Let's now open this problem to solve it. Let's go through and understand the given problem statement. Here it says, Chota Bheem wants to eat maximum number of Ladoos in Dholakpur on Independence Day. The houses in Dholakpur are arranged in the form of binary tree and Ladoos have Ladoos the same as their house number. Chota Bheem is standing at his home initially. Okay. Find the maximum Ladoos he can eat if he can go to the houses within a maximum distance of k from his house. The number of Ladoos at his home should be included in the sum. Okay, so here it is said that we have to find the maximum number of Ladoos which Chota Bheem can eat on the day of Independence Day, and he can visit those houses which are located at the distance k from his house, and each house has that many number of Ladoos that is represented by the house number. Okay, so we have to find that what is the maximum number of Ladoos he can eat. Okay, so here in note it is given that each house has a distinct Ladoos in it. Okay, so let's go through the given examples here. So first example says that this is the structure of the binary tree which represents the house in the Dholakpur, all the houses in the Dholakpur. So here it is said that home is equal to 9. That is Bheem's current position is at node 9. That means his house is located at node 9, and there he can get 9 Ladoos. And what all houses he can visit? He can visit all the houses which are located at a distance 1 from his house. Okay. So initially, here the output is 22. How we got 22? Initially Bheem at 9. So sum is equal to 9. In second move, he went to 5 because again from 9 we have to take one step. So he went to 5. So the sum became 9 plus 5 equal to 14. In the third move, he went to 7. So here, so till now we have got the sum as 14. So in 14 we will add 7. So that is 21. And in fourth step he went to 1. That means from this house to this house. So here we can see the sum is 21 plus 1, that is 22. So within k distance, Bheem can get 22 Ladoos. So we're starting from this 9. We have to look all the nodes which are located at distance k. That is here k is 1. 1 distance from this 9. So we can see 1 plus 5 plus 7, and even we have to add all the Ladoos which is present at his home. So we have to include 9 as well. So the sum became 22. Okay. So if you look at the second example, so here the houses are represented using this binary tree. Here it is said that home is 40. So Bheem's home is at node 40, and he can travel maximum 2 distance from his home. Okay, so from this 40th location, he can travel to these 2 homes, then on the right side this one. If you see all other nodes, so it will be at a distance, if you consider this 8, it will be at the distance 3 from 40. So we will not consider that. So all those houses which are falling within the range of 2, Bheem can visit and have all the Ladoos from there. So if you can see, if you add all of these, then we get the sum as 113. Okay, so I hope the problem statement is clear and even both the examples are clear. So for solving this problem, since it is given in the form of binary tree, so we will be using a binary tree and performing a traversal on it. We can start the traversal from the root node of the binary tree and traverse the tree recursively. We can keep track of the distance of the current node from the given home node. Okay, if the current node is at distance k from the home node, then we can add the number of Ladoos in that node to the sum. If the current node is not at a distance k from the home, then we can recursively traverse the left and the right subtree of the current node. While traversing the left and the right subtrees, we can keep track of the distance of the current node from the home node. If the distance of the current node from the home node is k, then we can add the number of Ladoos to the node in that node to the sum. Otherwise, we can continue traversing the subtree until we reach until we reach a node at a distance k from the home node. Finally, we return the number of Ladoos obtained from the nodes at a distance of k from the home node. Okay, so this approach we will be using for solving this problem. So how can we apply this approach to this one? So we will start with initially first node here. Okay, so we will check if this node is matching his home node, then it is not. Then what we'll do, we will search in the left subtree. We will search in the left subtree for this one, for this current node with distance k, that if it is present in k distance. So it will first look for k distance for node 1. Then if it is not present, then it will go inside this one, this left subtree, and it will continue recursively searching until it traverses the entire tree in search of that node. Okay, so if it is not present in the left subtree, then it will try finding it at right subtree. Okay, right subtree again at distance k. If it is found at distance k, within distance k of in the right subtree, then what it does, it includes the summation of that the value of that node to the sum variable, and start iterating all the nodes located at particular distance. Okay, so here it can see that from this node 1, here we can see that yes, that target node or a home node is present at location 1. So from this node, since it is located at distance 1, so this 1 is included in the sum. So once we reach here, then we see yes, it is matching. That means the current node is matching the value of the home node. So 9 will be included in the sum. So it will become 1 plus 9 is equal to 10. Then from this node, we will recursively traverse left subtree and right subtree. Okay, and find the sum of all the values of all the nodes which is located at distance k from this current node. So we will get 5 and 7 from here, because here the k was only 1. So that's why here the output became 1 plus 9 plus 5 plus 7, that is equal to 22. Okay, so I hope the approach is clear. So with this approach only we will solve this problem. I have already prepared the solution just to save time in typing. Let me just copy it here. So okay, so here I'll explain what all the steps it is done here. So first we initialize a static variable to store the sum of the Ladoos, so that we are calling as total Ladoos. Okay, then in this one, this Ladoos function, whatever was there as the input function for this one, the driver function, here it will return the maximum number of Ladoos that can be collected. So initialize inside that one, whatever was the static variable we created in earlier, that we are initializing to 0. Then what we are doing, we are traversing the entire binary tree. Call the traverse function to traverse the binary tree and add the Ladoos. Okay, so and since this was declared as the global variable, so whatever the value updated inside this traverse function, that will be stored in the total Ladoos, and we can directly return the number of Ladoos collected. If we see this traverse method, then it is expecting 3 input, that means current node, target and k. So here we are first checking if the current node is null, then we return -1. But if the current node's data is matches the target data, then we add Ladoos for its subtree. Okay, so here since that is matching when we reach this node, just in case, then here it shows that no data matches with the target. So what we do, we call so here we call add Ladoos function. If you look at this add Ladoos function, we pass node and value of k here. So k's value is 1. So if you look at this one, so here we need to look at it carefully. So here what it does, it receives both those input. Here it checks if the node is null, if node is null or distance is less than 0. then we return. Else, if this is not the case, if you are not returning directly from here, then what it does, it adds the node data to the Ladoos. Okay, so right now I'm speaking about 9 and the below things. So I'm just speaking of that scenario. So once we have reached here, so the 9 will be added to this one. Then what it does, it calls left subtree, and it is saying that distance -1, and right subtree, it is again called distance -1. So when it will reach again, when it will be called again, so here the distance will be 0. Okay, distance will be 0. So here it will check if the node is equal to null, it is not null, and distance is less than 0. So even the distance 0 is valid here. So if it is less than 0, then only we will return. If it is not, then we will add that node data to total Ladoos. So 5 will be added. Similarly, in the next time we will see the node value is null here, so that is not correct. And for the right subtree, the value 7 will be added with the distance 0. Actually, one thing to take care here is that the distance 0 is considered here, that is the starting of the left and right subtree. So whatever the starting node of left and right subtree, that is considered as that node located at distance 0 from the current node. Okay, so if you are seeing this one 9, and we are looking this subtree which is on the left of it, then we can say that for this subtree which is starting with 5, this is having yes, since we are talking about the root node of that subtree, so we can say that it is at distance 0 only. That means 0 for that subtree until the distance becomes less, that means less than 0. So that point is valid here. So that's why we are calling it with distance -1. Okay, so until the distance become less than 0. I'm explaining this because in every part of the remaining code we have used the same thing only. Okay, so I hope this is clear that how we are calculating the below part 9, 5 and 7. That is once we match the target node. If that is done, so we will call add Ladoos. If this condition is not true for a particular iteration or scenario, then what it does, then we try to find out if the target node is not found at the current node subtree, then recursively search in the left subtree. So here now if you are initially at 1, it will search in recursively in this left subtree. Okay, so here it will try to find, yes, if it is located at distance k for that particular node. If the distance is greater than 1, okay, that means if the target node is found in the left subtree, then we add the Ladoos for the right subtree at the distance k -1. So suppose if you are having such something like this, if you consider this one, if this is the target node, then and if the maximum distance we can take is 2, so even it has to take the value of 7, though it is in the right subtree of this 9 node, then also it has to consider. So that's why this step is added explicitly, that if the target node is found in the left subtree, then we add all the Ladoos for the right subtree which is located at the minimum distance which is there, that is distance -1. So we will add all those things again, and for that we will again call add Ladoos function with the same approach, and after that we reduce the distance for that iteration so that we can check for the next one. Suppose initially we are checking for distance equal to 2, then next time we have to check with distance equal to 1, something like that. Then return distance -1, which is the remaining distance from the target node. Okay, so this was the one scenario. Another scenario, if the target node is not found in the left subtree, then recursively search in the right subtree. Okay, so here for this given example, this scenario is correct. So here, while being at 1, it checks if that node, the target node, is found in the right subtree. Then for one, right subtree starts with all this place, this one 9, 5, 7, all those things. So yes, here we will get yes, it is found in the right subtree. So what it does, it it adds that node value to the sum, that which is one here, and it performs that add Ladoos functionality for that value. So we will recursively add all the values, that means 1 plus 9 plus 5 plus 7. Okay, and if once this is done, then again we return minus the distance minus 1. But if the target node is not found in the current node subtree or its subtrees, then return minus 1. Okay, so this was the complete code of it. Only thing we need to take care is that whenever we are taking any node into consideration and we are looking at the left node and the right node of it, left subtree and right subtree from it. So the starting of the starting of that particular subtree, the first node of that can be considered at present at a valid distance of k, that is equal to 0, and that is considered if the minimum distance is required as 1. Okay, because the condition here is such a way, here it is not that distance is equal to 0 then return, no, distance is less than equal to 0 then return, because first we are adding the value, then only we are decrementing it. Okay, so first it will look in this left subtree, it will add the value 5, then it will decrement the value. First it will add the value 7 in this one, then it will decrement the value. That's why the condition is that way. Okay, so now let's try compiling this code. So here we can see we have got correct output here. Let's try submitting the solution. So here we can see we have got all the test cases covered. So this problem is solved successfully using this Java language here. So first I tried solving it with Java. And talking about this time complexity of this given solution, it is in the order of big O of n, where n is the number of nodes in the binary tree. In worst case, we may have to visit all the nodes in the binary tree, hence the time complexity is big O of n. The traverse function visits each node only once, and for each node, the add Ladoos function is called at most once. So the time complexity of the both function is also big O of n. In terms of space complexity, if the solution uses big O of h space in the call stack, where h is the height of the binary tree. In the worst case, the binary tree may be a skewed tree, in which case the height of the tree will be n. Hence the space complexity will be in that case big O of n only. However, in the balanced binary tree, the height of the tree will be log n. Hence the space complexity will be big O of n log n if it is balanced subtree. Okay, if it is a balanced binary tree. Okay, so this was the Java solution of it. I have even prepared C++ solution. So let me go to the C++ editor. Let me copy that C++ code here. Here again the logic is completely same, just the syntactical difference between C++ and Java that is followed here. So here also we start with this Ladoos function, then we initialize total Ladoos as 0, then we traverse, and in traversal also we are checking all those conditions here. Then and for adding the Ladoos, again we are first adding the data, then we are reducing the distance. That's why whatever is there even at the 0 distance, that we are considering it as valid scenario. Okay, so let's try compiling this code. So even for C++ code we have got correct output. Let's try submitting the solution. So for this also in C++ we have got all the test cases covered. Okay, so this problem has been solved successfully using both C++ and Java. So I'll provide the link for this question and the link for the solution code in Java and C++ in the description box. Please do check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.